All right, hi everybody. Welcome back to Math Background for Machine Learning. When we ended last time around, we were talking about mean and variance for vector-valued random variables. And so there were a couple of questions about that posted on Piazza, so I figured I would add a little bit of explanation beginning of this class, and I've posted some extra lecture notes at the end of the lecture notes on mean and variance. So let's take a look. So if you remember, the variance of a random variable that's a vector is a matrix, and it's defined here. And in theory, at least, that definition tells you everything you need to know, but obviously it takes a little bit of working out to figure out what that means. So let's take a look at how to actually interpret a variance matrix. So it's easiest to do in the case of a random variable that is like 2 or 3 dimensional, because that way you can plot the random variable and see what happens. But the principles are exactly the same no matter how many dimensions are in your random variable. So let's take a 2D example like this one here in the lecture notes. So what I've done here, I've made what's called a scatter plot. So that means that I've taken a bunch of samples, if I have an experiment that's described by the random variable x, I just repeat that experiment, in this case 150 times, and I get a whole bunch of copies of x, each one following the same distribution. And I can calculate the variance of x. And I can also make a plot. So here I'm plotting x1, the first component of x, versus x2, the second component of x, for each of the 150 copies. So each one of these 150 copies is a little circle on the plot. And so you can see here, right, that the distribution is centered around 0, 0. So it's each sample is a 2-dimensional vector, and on average the sample in the middle is 0, 0, and that is in fact the mean of this distribution. And if I were to have a non-zero mean, it would just shift the distribution left or right. So for example, if I increase the mean in x1, it'll move it over to the right, and if I increase the mean in x2, it would move it up on this plot. And then the variance tells you something about the shape of this scatter plot. So in this particular example, the variance matrix is given right here. It's a diagonal matrix with 2 and 2 on the 2 diagonal components, and diagonal means that the other components are all 0 of that matrix. And so you can see I've got sort of a round distribution, meaning that the spread is about the same in any direction. So if you look at the spread left to right, it's the same as the spread up to down, and it's the same as the spread diagonally, right? And that, in fact, is exactly what you'll get with a variance matrix that looks like this, a diagonal matrix where the same element is in every diagonal entry. The amount of spread, basically, so if you look here, right, on the x-axis or on the y-axis, you can see that a typical spread is about from -2 to 2, right? There are some that are more, some that are less, but it's about typical. And so a typical spread is actually about square root of 2. So you can see, so square root of 2 is about 1.4. And you can see that that's, maybe there's roughly half below and half above. What happens is actually it comes from the definition of variance. The mean of the squared x-coordinate, horizontal coordinate, is going to be 2, right? That's exactly what it means. So on average, a typical entry is going to be about square root 2. Now, if instead we start to have different elements on the different diagonal entries, that's going to scale the distribution. So here's a variance matrix that has 1 in the first diagonal entry and 3 in the second one. And you can see that it's squashed skinnier in the x1 dimension, and it's fatter in the x2 dimension. And that's in fact exactly what we'd expect. So in general, if you scale a diagonal element by a factor of sigma squared, that scales the typical spread by sigma in the corresponding direction. And so you can see, for example, we made the x2 spread bigger, and so it's spread bigger in the vertical direction, and we made the x1 spread smaller, and so it's narrower in the horizontal direction. All right, and so there's one last ingredient to interpreting variances, and that is transformations. So if you look here, if you have a random variable x and it has variance sigma, then you can make another random variable. We'll call it y. So we'll write here that y is equal to a times x. So here x is a vector in R2, and a is a matrix, so it's going to be a 2 by 2 real matrix. And it turns out that you can prove that if the variance of x is sigma, then the variance of y is a sigma a transpose. And that's not actually too difficult to prove. We might do it in a second. But what that is going to let us do then is it's going to let us understand random variables by using transformations to make the variance matrix simpler, right? So if we have some general variance matrix with non-zero entries everywhere in the matrix, that's going to wind up potentially having not being all that easy to interpret on its own. But if we can use a transformation, a linear transformation like this one, y equals ax, to make the variance matrix look simpler, then we're going to be able to understand it. So all right, so let's just do that proof, because it's kind of a neat little proof. So the definition of variance, right? We have that the variance of y is equal to the expected value of y minus the mean of y times y minus the mean of y transpose, right? And so I told you before that the mean of x was 0, and so the mean of y is also 0, because anything times 0 is 0, so a times 0 is 0. So this is just equal to the expected value of y times y transpose. So I'm dropping all the y bar, which is 0. And that's equal to the expected value of, well, y is equal to ax, so that's ax, and then y transpose is x transpose a transpose, right? And so I've just substituted in the definition of y in terms of x. And now I'm going to use linearity of expectation. We talked about that before, but it means that anytime you take a linear function of something, you can just pull it outside the expectation. So that means that we can pull out this a on the left, a times the expected value of x transpose, and then there's another a transpose, and we're going to pull that out on the right, like that. And then we know what this is, right? E of x transpose, that's by definition the variance of x, which we called sigma, right? And so this is equal to a sigma a transpose, right? And so that is, we're actually going to get, hopefully later this lecture, into more material on linear algebra, but that's a nice preview of how to use linear algebra in combination with the probability stuff that we've been talking about. And it shows that the variance of y is this thing. And so that's going to let us interpret a general variance matrix. So here's an example of a scatter plot of a random variable with a general variance matrix, right? So here's the scatter plot, and here's the variance matrix. And in order to interpret it, it's going to help to factor the variance matrix. So a factorization is just something like this. The variance matrix is equal to a product of some other matrices. We're going to, in order to interpret variances, it turns out that the most useful factorization is something called the singular value decomposition, or SVD. And that looks like this. The variance matrix is the product U times S times U transpose, where U is an orthonormal matrix, meaning that its columns are orthogonal and the norm of each column is 1. And the matrix S is diagonal. And you can see why that might be helpful, because we already know how to interpret diagonal variance matrices. And so if we take the singular value decomposition of this variance matrix, I'll actually just copy it out of MATLAB where I put it together earlier. Let's see. So if we define U is equal to root 2 over 2, root 2 over 2, root 2 over 2, and root 2 over 2, but we're going to make this one negated. And if we take S is equal to the diagonal matrix 3 and 1, like that, then U transpose should equal our sigma from before, which is 2, 1, 1, 2. All right, and so yeah, so that's the singular value decomposition of this matrix here, and so what that means then, if our this was defined to be the variance of X was sigma, and so if we take the variance of U times X, right, that's equal to, of U transpose times X, that's going to be equal to U transpose sigma U by the transform rule that we talked about earlier, which is equal to U transpose U S U transpose U. And that's the identity, and that's the identity, so we just get S. So that means that we've transformed X into U transpose X, and the variance of U transpose X is this diagonal matrix S right here. And that's nice because we already know what the scatter plot of that looks like, right? We had that right here, right? And so how is U transpose X related to U? Well, orthogonal matrices can do things like rotate or flip, but they don't change lengths or angles. And so what that means is that the variance of U transpose X, this thing here, is a rotated or possibly flipped version of the variance of X. And so if you look at X here, right, it looks like if you rotate it about 45 degrees counterclockwise, which turns out to be basically what U transpose is going to do here, you'll get this plot, right? So the recipe for understanding the shape of a general distribution based on its variance is to make a factorization of the variance matrix, like the singular value decomposition here, use it to make a transformed random variable that has a simple shape, like a diagonal variance matrix, interpret that, and then transform it back. All right. So that was everything I wanted to say about variance matrices for now. We're going to get back to those later in the course, but I think it's a good time now to move on to the next topic. As always, please. Oh, there's a question on Piazza. Somebody wants to know if we're going to go through how to find a singular value decomposition later. The simplest answer is you call the singular value decomposition function in Python or MATLAB. And for the purposes of this course, that's actually the best way to do it. It's actually a really interesting numerical problem to write numerical code to calculate the singular value decomposition, but that's definitely outside the scope of this course. So yeah, I think what you need to know about calculating the SVD is just that there's a function for doing it in just about every programming language or some library attached to that programming language. And it's actually a really nice decomposition in the sense that it is very stable to be able to calculate it. So really, the best advice is just, call the function, enjoy the result. Don't worry too much about the algorithm that got it. Unless you're interested in that sort of thing, in which case I encourage you to look up numerical methods for it because they are actually kind of fun. All right, keep asking more questions on Piazza, as always. And let's move to the next topic. All right, so as always, these lecture notes are all linked from the lecture schedule post on Piazza, so feel free to load it up and follow along. I'm going to hit refresh just to make sure I have the latest version. There we go. All right, so we talked last lecture about how to work with probability distributions. And I wanted to, because it's a little bit complicated, I wanted to review some of the notation that we used, because we're going to be using that a lot for the rest of this lecture, and so if it's giving you troubles, then you're going to have troubles following the rest of this lecture. So, so here goes the review. So let's say that we have three random variables, x, y, and z. We write p of x, y, z for the joint distribution of x, y, and z, and we think of that as a probability table where there's one mode, one dimension for each of the random variables. It's labeled with that random variable. And then we have a tensor with that many modes. And each entry of that tensor is an entry in that joint probability distribution. So for example, if we look at the ijk entry in the tensor, right, so there's three modes, so we specify one offset for each of those modes, we get the number, the probability that x is equal to I, and y is equal to j, and z is equal to k. All right, so that's the representation of a probability distribution. Given that representation, then we can slice it. So what is slicing? Slicing a tensor means you fix an index in one of the modes. So let's say the y mode. So we could fix the y equals 1 index and then take all possible values of the other two indices, right? So that corresponds to every value of x, only the value y equals 1, and every value of z. And so that's a two-mode tensor. It's got a mode for x and a mode for z. The mode for y has gone away because we fixed the value to just a single value of that mode. And the ik element of that two-mode tensor, of the slice, is the one where x is equal to I and z is equal to k, and y, of course, is equal to 1 because that's true for every element in this slice. All right? So let's see. So for conditional and marginal distributions, we can do the same thing. So here, for example, is a conditional distribution, the probability of x and y given z. And so that's a table, again with three modes. It gives you the conditional probability for a particular value of x and a particular value of y given a particular value of z. And so we can slice that to get a two-mode table here by fixing z equals 1. And so that's a conditional distribution of x and y after we observe the event that z is equal to 1. Or we could slice this way, p of x comma y equals 1 given z, and that's also a two-mode table, also a slice of the same larger table. But there's a difference, right? This first one, p of x, y given z equals 1, is itself a probability distribution. It's the distribution over x and y conditioned on a particular event. This second example is not a probability distribution, right? It's got elements of several different probability distributions in it. And so if we summed over all values of x and z, we would not expect to get 1. We might just by accident if we were lucky, but we wouldn't expect it to be true. All right. So let's see. Oh, we have another question from Piazza about whether the proof of variance transforming, the proof that I went through using linearity of expectation, about whether that would be a proof that we would go over in 601 or 701. That would be something likely that we would go over very quickly in 601 or 701 and then use it for other purposes. So you might expect, for example, that instead of proving that the variance changes in a particular way when you transform a variable, the professor would just write down that formula and use it to go through the plots the way we did and show the shapes of the variances, the shapes of the scatter plots of the different distributions. Yeah. So keep asking those questions on Piazza. And keep asking questions on Piazza about tables and slicing, because we're going to be using that representation for the rest of this class. All right. So these tables, right, we've been using small ones, you know, tables with 3 modes where each mode has 2 or 3 values, something like that. When we're dealing with a real example in machine learning, we don't have any such luxury. So for example, we could have a table with 1,000 different binary variables representing a joint distribution over 1,000 things we might observe. And even when the variables are only binary, that's going to have 2 to the 1,000 entries in that probability table. And if you're not familiar with the number 2 to the 1,000, well, I would not recommend trying to count up to it or to store that many things in the memory of your computer, right? It's a completely unmanageable number. And so we're never ever going to want to write down that probability table. Nonetheless, it makes sense to think about it, because that's sort of, it's a complete representation of that joint distribution, and we can work mathematically with it even if we can't handle it computationally. So we have a couple more questions from Piazza. Oh, somebody wants to know if we're going to learn about discrete probability distributions like Bernoulli or Poisson. Yes, so that's actually a topic that we're going to cover either at the end of 606 or the beginning of 607. There was a follow-up question about whether those distributions would have uses in machine learning, and the answer is very definitely yes. I mean, machine learning is all about using probability distributions to model things that are going on in the world around you. And so knowing the properties of, you know, common families of distributions is very helpful in selecting which distributions to use to model things. That is actually going to be one of the key topics of a course like 601 or 701. So we're going to, you know, scratch the surface here in math background, but like that's, you know, that's going to be an important activity throughout 601 and 701, is using distributions to model things that are going on in the world. All right, so getting back to these gigantic tables. So if we actually want to store a joint probability distribution in the memory of a computer or write it down on a piece of paper, we're going to have to go with a form that is not as large as, you know, 2 to the 1,000 entries. In fact, 2 to the 1,000 is going to be kind of a small joint distribution. We might have a distribution over, well, for example, it would be pretty common to have a data set where you have, you know, 1 million different real numbers, and each of those real numbers you represent as a 32-bit value, and so that's 2 to the 32 million bits worth of indices into your table, right? So just specifying an index into that table would require a million floats, which would be, sorry, it'll be 32 million bits to index into the table, and so the number of entries is 2 to the 32 million, which is, 2 to the 1,000 was mind-bogglingly large, and 2 to the 32 million I don't even want to think about. All right, so if we want to represent a distribution over a lot of random variables, we have to use some compact representation. And as always, if we use, so we're always going to wind up using, or almost always going to wind up using lossy compression. We're not going to be able to losslessly compress a probability distribution. And so we'll use some kind of lossy compression. And as always, there's going to be a trade-off between how accurate the representation is and how big it is. So we'll be able to get, a small, pretty decent representation, or a medium-sized, quite good representation. But if we wanted exact, we would have to go back up to the 2 to the 32 million, which we're just not going to do. And so the most common compressed form is what's called factored form. And again, this is a topic that is going to be covered in much more depth in 601 or 701, but it's something that I think is helpful to think about just as a precursor to those courses. So we have another question from Piazza. Okay, so somebody is asking, what is the difference between these two things? P of x comma y equals 1 given z, and P of x comma y, x comma z given y equals 1. So, excuse me. I think that's a good question. So let's actually do an example out in a bit more detail. So let's start by writing out P of x comma y. Sorry, that's an x comma y comma z. So that is going to be an element of our 2 by 2 by 2, right? So we're assuming that x, y, and z are binary variables, and we're going to have an x index, a y index, and a z index into the table, and so there's going to be 8 entries total. So we'll write it out something like this. So x, y, x can be 0 or 1, y can be 0 or 1, and we'll y 0 or 1, and we'll have over here this is z equals 0, and over here this is z equals 1. So we're going to have 8 different numbers. Let's say 0.1, 0, 0.2, 0.4, okay, that adds up to 0.7, so we have 0.3 left, so we'll make it 0 and 0.3. So unless I have, that should add up to 1, hopefully. And so this is a probability distribution over x, y, and z, 3 different binary variables. And so, for example, the probability that x is 0, z is 0, and y is 1 is this element, meaning 0. So it's impossible to have x be 0, y be 1, and z be 0 all at the same time. All right, so this is the joint distribution. And let's look then at this. Actually, let's look at this conditional distribution first, right? So, this conditional distribution, we're going to condition on y equals 1, right? So what we're going to do is, let's make a copy of this table, right? So 0.1, 0, 0, 0.2, 0, 0.4, 0.3, right? And I'm not going to copy the labels, but they're the same as they are over here. So if we condition on y equals 1, that corresponds to these elements and these elements, right? because this one is y equals 0, right? And this one is y equals 0. So what we're going to do when we condition on y equals 1, we're just going to cross out all of the elements where y is not 1, and then renormalize, right? So this sums to 0.9, it looks like. And so we're going to, after we renormalize, we're going to get a table that is 0, 2 over 9, 4 over 9, and 3 over 9, which is a third, but I'm not going to bother simplifying. And here, this axis corresponds to varying x. So this is x equal to 0 and equal to 1. And here we have z equal to 0 and z equal to 1, right? So that's this here, right? And we looked at how to do conditioning before, but this is an example of how to do it. All right, so, and you notice it's a two-mode table, right? It's got an x-axis and a z-axis. Right, and so that's this. Now let's look at this here. Well, so actually let's first look at p of x comma y given z, right? So that's going to be when we write p of x comma y given z, that means we condition on each possible value of z. So if we condition on z equals 0, that means to take this table and renormalize it so that it sums to 1. So we get 1/3, 0, 0, and 2/3. And then this and this one, and normalize it so it sums to 1. So we get 0, 4/7, 0, and 3/7. All right. And again, this here has the same indices as before, right? X is this way, y is this way. Sorry, for some reason it doesn't want to write my y's accurately. Oh, all right. Like that. And then z is the difference between layers here, right? And so now if we take, so this is a slice of this table, and in particular it's the slice with y equals 1. And so it's just this pair of elements and that pair of elements, like that. And so this here is the table 0, 2/3, 4/7, 3/7, and y is fixed, so it has just an x mode like that and a z mode like that. All right, so so hopefully that makes sense. Hopefully that helps to interpret what these tables are. All right. So yeah, we were at factored form. So basically the idea is we want a compressed form of a probability distribution, and we're willing to sacrifice some accuracy in order to get a representation that we can actually store in our computer. So let's take a look at an example of a factored form. So for this example, we're gonna look at the story of the rusty robot. So there are 5 binary random variables, which we're going to call O, M, R, W, and U. So O is whether our robot is outside, true or false. M is whether it's made out of metal, true or false. R is whether it's currently raining, true or false. W is whether our robot is wet, true or false. And U is whether our robot is rusty, also true or false. And so because there's 5 binary variables, we have 2 to the 5 or 32 entries in this table. And the table is represented as a tensor with 5 modes, and each mode having 2 entries in it. All right, but instead we can represent it in factored form. So I've written here the joint probability distribution here on the left, and then on the right I've written out a factored form here, and we're going to go into more detail about what this means, but basically it means that every entry in here we're going to work out as a function of the entries of some smaller tables, right? So here P of O is a table of the marginal probability distribution of O. And that just has two entries, right? Because it's got one binary argument. Same thing with P of M, P of R. Here's a conditional distribution of W given O and R, and another conditional distribution of U given W and M. And so I haven't addressed whether this factorization is accurate. It's probably going to introduce some approximation to be able to write it this way. But supposing that we can do it, if we sum up, we get 2 parameters for this one, 2 for that one, 2 for that one, 8 for this one because it has 3 binary arguments, and 8 for this one, again, 3 binary arguments. And actually, it's actually even a little bit smaller than that because one parameter is lost for the constraint of summing to 1 for each one of the probability distributions in here. So this is actually fewer than this, but an upper bound is that we have 2 plus 2 plus 2 plus 8 plus 8, which is 22 parameters in total instead of 32. Now, because I'm using an example that we can write out, put on the whiteboard in a lecture, we only have a little bit of savings from 32 to 22. But if we think of doing this in an example with 1,000 variables, we can get easily a savings of a factor of like 2 to the 950 or 2 to the 990, right? Which is a very, very big savings. And so it's well worth it to use this, this compact factored form. All right, so let's take a look now at the semantics of this expression, right? So I've written down an equality involving tables. And so the question is, what does that actually mean? Oh, and I've also written down an expression with multiplication involving tables. And so what does that actually mean? So the left-hand side is pretty clear, right? It's a table with 5 dimensions and 2 to the 5 entries right there. The right-hand side, the whole right-hand side, therefore must also represent a table of the same shape because 2 tables can't be equal unless they have the same shape. So this here, we're going to figure out a way to interpret it as a table with 5 dimensions and 2 to the 5 entries. And we're going to specify a recipe for building it out of the smaller tables. All right. So I've already sort of, I've gone through something like this before in response to a question, but basically a typical entry of a table. So if we want to index into a table, we specify a value for each of the random variables that are on the axes of that table, on the modes of that table. So for example, if we wanted to index into P of W given O and R, we'd have to specify a value for W, O, and R. And so here are a couple more examples of individual tables. So P of O would be a distribution over O. It's just 2 numbers that sum to 1. Excuse me. So P of O is a table with 1 axis, 1 dimension, 2 numbers that sum to 1. Here is P of W given O and R. It's 8 total numbers. And I've represented it as 2 layers, each of the layers being 2 by 2. So we have W equal true and false for the top layer and the bottom layer. And then within each one, the rows are O, the columns are R. And so this table here gives us 4 different probability distributions, right? For each possible value of O and R, we have a conditional distribution of W given that value. So for example, when O and R are both true, let's say that true corresponds, that it's false and then true. So O and R both true corresponds to this element and to that element. This element has W, let's say true on this side, and this one has W false, and so it's a probability distribution over W, 5% true, 95% false, for that particular value of O and R, okay? And so you can see that 0.5 and 0.95 sum to 1 because it's a probability distribution, but you don't, for example, get a sum to 1 over this entire table. All right, so if we want to interpret this expression, or any other expression that involves multiple tables, what we do is we look at all the random variables that appear free anywhere in the expression. So free means not inside an event. So if it appears anywhere free, then it's going to be a mode of the table. And so this expression here represents a table. There are 5 variables, O, M, R, W, and U, all appear free here. And so this represents a big table with 5 modes. That's what we hoped, right? Because we had an equality here where this thing was equal to a table with 5 modes, and so this had better also be equal to a table with 5 modes. All right, so to get a particular entry of the big table that's represented by this, what we do, so here's an example of a particular entry. We just fill in particular values for each of the 5 random variables. What we do is for each one of these little tables here, we use this assignment to fill in all of the random variables that appear in this little table. So for example, let's take a look at this term, right? P of W given O and R. Looking at this assignment, we would fill in W equals true, O equals false, and R equals true, and we'd get P of W equals true given O equals F and R equals true. And so we could look that up in this table, right? This is a table with 8 entries, one of which is this value right here. And we get a real number. And notice that when we did that lookup, we had to ignore some of the values in this assignment, and that's fine, right? We just use the ones that are relevant and don't pay attention to the rest. And so now for each one of these 5 little tables, when we fill in all of the assignments, we get a scalar. And so we get a scalar times a scalar times a scalar times a scalar times a scalar, and we know how to evaluate that, right? That's just ordinary real arithmetic. So that's a complete recipe for how to evaluate this expression to get a table with 32 entries in this case. And in general, we would never, like, if we're doing this to avoid ever writing down the full table, we would want never to compute out each entry of that full table. We would want to do something smarter to be able to avoid doing that. But if we needed to, we would be able to, according to these rules. All right. So just to reiterate, when we're looking for free variables, right, we want to skip over events that contain the variables. So for example, this expression, P of W given that O is false and R, that would represent just a 2x2 table because there are 3 variables, but one of them only appears inside an event. All right, so these rules, you know, they take a little while to describe, so let's describe them in another way to help maybe with people interpreting them. So this is called, this operation is called broadcasting. So we have these labeled tables, right, where each table has, you know, some number of entries and its modes are labeled with a random variable. And we're going to define all of the standard arithmetic operations, plus, minus, times, divided, that sort of thing. We're going to define them by a semantics called broadcasting, which means that whenever we do a binary operation on 2 labeled tables that are not the same shape, what happens is that we will effectively replicate the smaller table a bunch of times to match the size of the larger table. So here, for example, this table, which has only an x argument, added to this table, which has both an x and a y argument, well, the way we do it is we duplicate the x table. So we make a new table, which looks like this, 1, 2, 3, 1, 2, 3, and that's a table that has x on that axis and y on that axis. And this is actually the same table as this one, right? And the reason that's true is because this table doesn't depend on y. So it's got an extra spurious y argument that doesn't influence anything, but it's actually the same as this one. So this operation going from this one to this larger one is called broadcasting. And now this table right here is the same shape as this table. And so it's perfectly legitimate to add this table and that one. And if you do that, you get this one. So for example, the bottom right entry of this is 6, the bottom right entry of this is 3, and 6 plus 3 is 9, right there. And just like with a lot of the other operations that we've described, a lot of programming languages implement broadcasting either natively or in a standard library. So MATLAB and Python are both like this. There's a link to how broadcasting is implemented in Python from the lecture notes. All right, so this broadcasting is actually just a different description of this semantics here. Some people find one of the descriptions easier to understand, and other people find this other description easier to understand. So whichever one sort of fits in your head better, use that one. All right. So these factored representations, like I said, one of the things that we want to do is we want to avoid ever working with the distribution in its full uncompressed form. So what we want to be able to do is work with distributions in the factored form. And so there's a bunch of very useful operations that you can do on factored distributions. And so let's take a look at a few of them. So one of the first ones is the chain rule. Given a probability distribution in factored form, what the chain rule lets us do is manipulate it by splitting and recombining its factors. So in general, it is always true that P of AB is equal to P of A given B times P of B. And that is actually a direct consequence of the definition of a conditional probability. So if you have, so let's just show how that works for a 2x2 example, right? So if we have a table, a 2x2 table that has U, V, W, and X as its 4 entries for the 2 possible values of A and the 2 possible values of B. So if we want to make a table that conditions on B, right? So if we condition on B taking this value, right? So this is P of A, B, right? Then P of A given B will also be a table that has an A argument and a B argument. But for example, if we condition on this one, we'll get V over V plus, V plus X and X over V plus X. And then here, if we condition on this value, we'll get U over U plus W, and here we'll get W over U plus W, right? So conditioning went from here to here. And so each entry of this table is P of A comma B divided by P of B, right? So P of B is just V plus X or U plus W. And so we're dividing each entry like that. And so let's actually move that over here. And there's an equality there. Whoops. sorry. So there's an equality here, right? So this expression is equal to that expression. And so if you just rearrange this expression, you get this one right here. So what we've just done is, for the case of 2x2 tables, we've proven that the chain rule holds. And in fact, the exact same proof works for completely general tables. So all you need is the definition of conditional probability. And so what that means is that anytime we have a joint distribution in our factored form, we can replace it by this further factored form. Or we can go the other way. We can take this and replace it by the joint distribution. So suppose that we have a distribution over A, B, and C represented as P of A, P of B given A, P of C given B, the product of those three factors. Then we can take these two factors and group them together to get P of AB, leaving this factor, right? And then we can split this back apart in the other direction to get P of A given B times P of B, right? Instead of this way, we've got P of B on its own. And then we can do that again. We can take P of B times P of C given B and replace it by P of BC. And then we can split that apart to get P of C times P of B given C. So every single one of these expressions is equivalent. They represent the same distribution, and we've just refactored it using the chain rule. Okay, so we have a new question on Piazza. So the question is, how do we select elements in factored form? I'm not sure how to interpret that question. There's two possible interpretations. One is, how do we select which small tables to use to make the factored form? And the other is, how do we index into a particular entry of one of those tables? So I'll answer both just to be just to make sure to cover the bases. So the second one first, how do we select entries of the smaller table? That's this discussion here, right? So it's in section 4 of the lecture notes. So what we do is, for each one of the little tables, we index into it. So this product represents a big table, and an element of the big table is corresponds to an assignment to all of your random variables, and we index into each one of the small tables using the corresponding elements of that assignment. So that's the easier one. That's why I answered it first. The harder one is, how do we select? And the answer is that that's actually a really difficult question. Knowing what is the best way to represent a big distribution in factored form as a product of a bunch of smaller tables, that's actually a deep question in machine learning, and there's a lot of different algorithms to try and select it. So that's something that you'll cover a little bit in 601 or 701, and actually much more in a course called Probabilistic Graphical Models, which it's a later course in the sequence after you take 701. Somebody else was asking for a definition of a mode. So a mode of a tensor is just, it corresponds to one of the indices, right? So in a tensor, a tensor is a giant table that you index into with 5 different indices, or 10 or 3, depending on the shape of the tensor. And so a mode is nothing more, nothing less than just one of the indices. So a tensor with 5 modes means that you need to specify the values of 5 different indices to get you to an element of the table. All right, so let's go back down. So I want to get to Bayes' rule. So from the chain rule, right, P of A given B, we can represent it as, P of A and B together, the joint distribution. We can represent it either as P of A given B times P of B, or P of B given A times P of A. So if we divide through by P of B, we get that P of A given B here is equal to P of B given A times P of A divided by P of B. And so this here is a very famous law of probability, a rule for working with probability distributions. It's called Bayes' rule after the Reverend Thomas Bayes, who first described it. And there's actually an even more general form of Bayes' rule that allows us to condition on some side information C all through. So if you just add a conditioning on C to every term here, you get P of A given B comma C is equal to P of B given A comma C times P of A comma C divided by P of B comma C. And the derivation of this is almost exactly the same as the derivation of this, and it's a good idea to go through and do that derivation for yourself. So what I would suggest, I'm going to describe an exercise, and I think what I'm going to do is just end the lecture a little bit early and give you time to work on this exercise on your own, and then next time through we'll go through the solution to that exercise. So here it is. There's two random variables, G and S, for whether the sprinkler is on and whether the grass is wet. So the sprinkler is here, it's on a third of the time and off 2/3 of the time. And here, if the sprinkler is on, the grass is wet 3/4 of the time and not 1/4 of the time. And then if the sprinkler is off, the grass is wet 1/5 of the time and not 4/5 of the time. And so given these two inputs, you can use Bayes' rule to find the values of this table, right? And so that's the exercise. Just fill in this table, and we'll discuss how to do it at the beginning of lecture on Wednesday. Yeah, enjoy the problem, and we'll see you next time.